Huh?
Never knew.
I'm alright. It's kind of like a Friday, so it's pretty awesome.
I know it's my Friday.
A homework question was from 3.5 and it's number 11. And so this one is the derivative of a product, but we have 3 factors there. So when we use the product rule and do the first times the derivative of the second plus the second times the derivative of the first, that's the product rule. It's the first and the second kind of thing, right? So we just need to establish, you know, which 2 factors do we want to call the first or second, and then the other one's going to be the first or the second. So, you know, it doesn't. I don't think it really matters. Like we'll call the 4x squared cosine x the first, and then sine would be the second. So it's essentially you're going to have 2 product rules to do this problem. So when we find y prime, we have to do the first times the derivative of the second. We'll just write it here. Plus the second times the derivative of the first. Is that all right? So again, that's why I recommend writing out, like when you say the derivative rule, when you say derivative, like write that symbol out. And so this is the derivative, but since we have other derivatives in that, we need to do a little bit more work to find y prime. So it just boils down to then finding these derivatives and putting them in place of that notation. So the derivative of sine is what? Derivative of sine is cosine. So that's going to go there. And the derivative of this thing, 4x squared cosine x, that's another product rule. So to take that derivative, we're going to do first times the derivative of the second plus the second times the derivative of the first, which is derivative of 4x squared. So like we can just put this one back into our original derivative. There aren't any derivatives in that. Again, here with that second product rule, we have to look at the derivative of cosine. 4x squared times the derivative of cosine is...
Negative sine x.
Which one?
Negative sine x.
Yeah, negative sine. So we're going to have our negative sine multiplying the 4x squared plus our cosine x times the derivative of 4x squared so we have this being the derivative of our, I guess our, what we call our first in the original function. So those 2 just get inserted in our original derivative and we're done. I mean, we're done with the derivative. We might have to simplify, but questions? If there's 4 things multiplied, then you've got 3 product rules you have to use. I don't know if MML will accept that.
I don't think it, well, I think it wants it, the sign distributed in, and I think if anything combines to do that.
Yeah, so I think this is fine for like an exam question. Something like that's totally fine. Oh no, we have a cosine squared and a negative sine squared. So I don't know. I mean, that we might be able to simplify it a little bit, but that's pretty much it. Any other homework questions? All right. Well, then we left off introducing 3.7 and what we were going to be doing in 3.7. So this rule in 3.7 allows us to take the derivative of composition of functions. And there were 2 versions here. First version, as we said, involved a substitution. And the second version, we wrote down sort of in words what it meant. So version 2, we wrote down the derivative of a composition. We take the derivative of the outside function, leave the inside function alone, and then we multiply that by the derivative of the inner function. So when we say outer function and inner function, sometimes that applies if you've got like 2 functions, one put inside the other. Something like e to the tangent x squared, we could think of as like 3 functions being put together. So it's, whether we're utilizing version 1 or version 2, like it's really important to be able to, identify sort of the structure of the function. And I think the easiest way to remember like the inner function is just imagine that you're going to plug in a value for x. And so like if we plugged in a value like x equals to 0, in either one of those functions, what would we have to do first? That's going to be your inner function. So like if I plugged in 0 into this function here, well, the first thing I have to do is take the sine of that. So the sine is my inner function. If I plugged in 0 in here, the first thing I have to do is square that. So we can think about that as our inner function. It's a little more complicated with like 3 functions, like this one here, e to the tangent x squared. But just think about the inner function as what function would you apply first if you had to plug in a value for x. And then the outer function is what you do second, like square root or raise e to that power or whatever. Okay. So version 1, we'll look at the first couple of problems with version 1 and 2, and that way you can decide which one you like. I don't have a preference which one you use, they're both totally valid. But version 1 does involve a substitution, and it does tell us that the derivative of our function y with respect to our variable x is the derivative of y with respect to u times the derivative of u with respect to x. And let me see how they wrote it up in the theorem. Y is f of g. So when we say y is f evaluated at g of x, again, the substitution here is we're going to let u, or whatever letter, we're going to let that equal to the inner function. The inner function of f evaluated at g of x being g of x. If I plug in for x, I have to first evaluate it at g. So that says we're going to let u equal to g of x, and I think that's stated in the theorem as well. Which then means y becomes a function of u, because we're letting g of x be u. And so we're looking at these two things to compute the derivative of y with respect to u. We're computing y prime. So y is a function of u. So when we take the derivative of y with respect to u, we're looking at this piece right here. And then the derivative of u with respect to x is this piece right here. So once we find those two things, we've got to multiply those together. And I think it'll make a little bit more sense once we look at concrete examples. That's the basic idea. The issue that we run into is when we take the derivative of u with respect to x. I mean, I guess it's not really an issue, but the thing we've got to be careful of is the derivative of u with respect to x, that's going to be a function of x. The dy over du is going to be a function of u, right? So the variable on the bottom of our notation is kind of the variable that shows up in that particular function. So dy over du is a function of u. You're going to have this function of u times this function of x, and you have to resubstitute based off of your original substitution. So this u being that function needs to be resubstituted as like the final step. All right, so we'll look at a couple of examples. Find the derivative of 3x plus 5 to the 100. And so we'll look at version 1. Version 1 involves a substitution. We're going to let u be the inner function. What would the inner function here be?
3x plus 5.
3x plus 5. Do y'all agree? So u is 3x plus 5. After you make that substitution, you want to rewrite y in terms of your substitution. So this step implies that y is now u to the 100th. Okay, and then we take the derivative of our substitution, u, and then we take the derivative of y in terms of u. So basically here we're finding u prime. du with respect to x, derivative of u with respect to x, or u prime. That derivative is just 3. And the derivative of y prime, the derivative of y with respect to the variable u would be 100 u to the 99th. And then we need to multiply those two things together and then resubstitute for u. So dy over dx is right here. The order they had it, du over dx was second, but it doesn't matter because we're multiplying. Dy over du. So we have the derivative of our original function is this 100u to the 99th times 3. Which is 300 u to the 99. And then we make our substitution back in terms of the original variable, which was x. So since u was 3x plus 5, that's what we want to put in here. This is 300 times u to the 99th, and that's the derivative of that function. You know, another way, we can also write it like this, just to kind of see each step individually. Because this is, when we utilize version 2, we're kind of doing all of this at once. We'll put the 3 over on the other side, I think. Okay, so that's the same thing, we're just going to write it like we have it in this box. Are there any questions on that? The second version says that we have this function here. To find its derivative, we have to take the derivative of the outside function, but leave the inner function alone. Okay? So our outer function here is there's just something to the 100th power. How do we take the derivative of that? We use the power rule. So the original power comes out. We take 1 away from the power. So there's the derivative of the outside function, but we want to leave the inside function alone at this point. So the derivative of the outer evaluated at the inner. And then we multiply all of this by the derivative of the inner function. And you see we get the same thing, right? 300 times this quantity. We see that's exactly the same as what we got in version 1. So honestly, version 2 is faster. You don't have to make substitutions and then resubstitute. But I think, like, when you're initially starting out, version 1 can be pretty helpful to sort of get your bearings with all of this. But this chain rule that we're utilizing for these types of functions, we actually have been using with like powers of x. We've been using when we took the derivative of cosine or sine of x or whatever. So I'll come back to that page, but when you were asked to take the derivative of something like x to the 4th, we can think about that as, you know, something being raised to the 4th power. So you've got like 2 things going on. You've got your input and you've got raising that to the 4th power. So when we say take the derivative of the outside function, leaving the inside function alone, right, we get that. But what we didn't do is say multiply by the derivative of the inner function, because in all of those, our inner function was just x itself, and you just get 1. So that's sort of a step we didn't actually address, but technically it was happening. Or when you take the derivative of the sine, so we take the derivative of the outside function, leave the inside function alone, and take the derivative and multiply that by the derivative of the inside. Again, it's just cosine x times 1. So I don't know if that's helpful to view it that way, but that's kind of what we've been doing with all of these so far. It's just when you know, the function that involves variable x is something other than x itself, then you gotta really consider what is the derivative of the function with x involved. Because up to this point, they've all been 1. The derivatives have all been 1. Okay. Example 2, we have the square root of x squared plus 1. And so again, version 1 requires us to make a substitution. We're going to let u equal to the inner function. The inner function here being x squared plus 1. So we're going to say u is equal to x squared plus 1. So you make your substitution with version 1, and then you rewrite the original function in terms of u. So from this substitution, we have y is equal to the square root of u. Or u to the 1/2. So substitute, reformulate the original function in terms of u, and then you just take the derivative of both of those things and multiply them together. So we're going to take the derivative of u with respect to x, which just gives us 2x. And the derivative of y with respect to u. Again, just a power rule there as well. 1/2 times u to the negative 1/2. And then you can resubstitute at this point. Once you find dy with respect to u, you can plug in our u, x squared plus 1 back in for that. But either way, we need to multiply these two derivatives together to get y prime. Okay, so we've got 2x times our 1/2 u to the negative 1/2, which our 2 and our 1/2 are going to multiply to give us 1, so we have x times u to the negative 1/2 and u was x squared plus 1. So that's our derivative there. Any questions about that? Okay, square root of x squared plus 1. Version 2 says we're going to take, well, let's rewrite the function first. It's x squared plus 1, and it's that quantity to the 1/2. So we take the derivative of the outside function, and we have to leave this inside function alone. So the derivative of the outer, we're just going to apply the power rule. 1/2 comes out front. Subtract 1 from the original power. So derivative of the outer with the inner function left alone, and then we have to multiply that by the derivative of the inner function. Does anyone have any questions? This is like a really important rule. There's you know a lot of things going on when you have composition. The next section depends entirely on us being able to use a chain rule. So we have this 1/2 times the quantity x squared plus 1 to the negative 1/2 times the derivative of x squared plus 1, which is 2x. So once again, combining the 2 and the 1/2, we have our same result we had above from version 1. So remember the derivative when we find it, what does this represent? Like what is this? When we say that this is y prime, when we say that's the derivative, what does that mean? What does that tell us? The slope of the original function, yeah, so the slope, what's the slope of this function at any x value, right? If I said, what's the slope of the square root of x squared plus 1 at x equals to 2, then you would just take your derivative and plug in 2 for x. You got the slope at that point, and so forth. So, a lot of times we're just focused on finding the derivative, but the context of the derivative doesn't change. It's still the slope of the tangent line at any point on the original graph. It's still the instantaneous rate of change at any point on the graph. Okay, function y equals e to the power of sine x, also a chain rule. Yeah, if we're going to identify the inner function for version 1 to make our substitution, we just think about what we would do first. If x is like 5 or 0 or whatever, we have to first evaluate sine of that. So that's the first function we would apply. That's the inner function of this composition. And then we rewrite the original function back in terms of our substitution. We take the derivative of both of those things and multiply them together. So du over dx is cosine x. And dy over du is still just e to the u. So our derivative in y prime is cosine x multiplied by e to the u, or cosine x times e to the sine x, because that was our u. Any questions about that? Okay. Version 2. Oops, sorry, wrong one. We take the derivative of the outer function, leaving the inner function alone. So again, with version 1, you explicitly identify the inner function. If you're going version 2, you're just sort of like keeping it in your head, like, what's my inner function? It's sine x, same as what it was with version 1. So if I take the derivative of the outer function and leave the inner function alone, I know that that inner function up here as the power has to be left alone. The derivative of the outer function is e to something. And so that's just e to that same power. Derivative of the outer with the inner function left alone. And then we multiply that by the derivative of the inner. So we have e to the sine x times cosine x. So I think it's important to remember like the derivatives with e to some power. Based off the chain rule, if we take the derivative of e to any functional power, we're always going to get what we have here. It's e to that same power times the derivative of the power itself. So I think that's worth remembering because, you know, exponentials, they just look weird with comparison to other functions. You know, their arguments are up here. Like find the derivative of e to the 3x. So the derivative of e to any function power is still e to that power. When we take the derivative, it's still e to that power, but we multiply by the derivative of the power as well. So that's, the derivative is just 3e to the 3x. With any exponential function, you're always going to have that original y or f of x that will always be in the derivative itself. So even though we're taking the derivative of 3 to the x, we see that the derivative, or sorry, e to the 3x, we still see the derivative involving e to the 3x. So all exponentials will be that way. What's the derivative of e to the negative x?
Negative e to the negative x.
Negative e to the negative x, yeah, because we have the derivative of e to any power, we'll say, is e to the same power. And this is just functional powers. E to that power times the derivative of the power. So we're taking e to the negative x and multiplying it by the derivative of negative x, which is negative 1. So we have this rule that shows up in 3.7 that says if y is e to kx power, where k is any real number, then the derivative of that's going to be what?
K to the kx.
Yeah, it's just k times e to the kx. But again, that's solely based upon the chain rule. What we wrote down here in red. Derivative of e to any power is still e to that power times the derivative of its power. So how about y prime for e to the negative 0.01x?
Wouldn't that just be negative 0.01 e to the negative 0.01x?
Right. Negative 0.01 times e to the negative 0.01x. So I know we're looking at a couple of things here with like e to a linear function kind of thing, right? E to the mx power, or e to the kx power. The other situation is here in red, but this, what we wrote down in red applies to any function of x as a power of e. So like that's that latter example where we have e to the x squared, or e to the 3x cubed minus x squared plus 1 power. You know, that's, the red one is more appropriate to think about than thinking about e to the kx, because that's clearly not the case with example 5 and 6. So the e to the x squared, the derivative of that would still be e to the x squared, but we have to multiply by the derivative of the power. So 2x e to the x squared for that one. Does that all make sense? So, like, I think it's just easier to remember that than have to do the first version of the chain rule over and over and over again, like e to a power. Again, we're talking about e to a functional power. We'll look at it, like, the derivative of e to the third would be what? 0, because it's a constant, right? I mean, we can still think about it, okay, well, y prime is just e to the power times the derivative of the power. What's the derivative of 3? 0. So you have e cubed times 0, which is 0. But it's easier just to recognize that as a constant. Derivative of any constant is 0. So I mean, it still kind of works there, but. Yeah, how about the derivative of e to the 3x cubed minus x squared plus 1? Yeah, go for it.
It would be 9x to the second power minus 2x times e to the 3x cubed minus x squared plus 1.
What do y'all think? You put that there because it's e times both of them. Derivative is e to the same power. We just copy that down, and then we just multiply that by the derivative of 3x cubed minus x squared.
Are we gonna get like double? And we have to use like the chain rule like 3-4 times.
Yeah.
In this, in 3-7.
Yeah.
Or later on.
We'll see it. Well, we've got a couple of examples here.
Okay.
Yeah. So sometimes you have to use the chain rule more than once. Oops, sorry, 3x cubed minus x squared plus 1. Any questions on that with the e? The other exponentials we'll get later on in chapter 3, they're a little bit different. They have an extra factor that the exponential base e doesn't have. Okay, does anyone have any questions? Okay. So how about the secant of e to the x? What's the inner function?
E to the x.
E to the x, do you all agree? Yes, e to the x is the inner function. Now again, you just gotta recognize the structure of the function. Like a telltale sign that you gotta use the chain rule is that you just have, you have an x showing up one time, right? If this were y equals to the secant times e to the x, then now that's a product rule. So just, you know, sometimes it's very subtle, and you've got to be able to recognize that that's a product rule, but what we're actually dealing with is a chain rule. So we take the derivative of the outer function. We're going to leave the inside function alone. What's the derivative of secant?
Secant x times tangent.
Secant times tangent. So we have secant times tangent, but we're leaving the inside function alone at this point. And then what do we have to do?
Take the derivative of the inner function.
Multiply all of that by the derivative of the inner function. suppose that's the derivative there is just e to the x. We'll just put that here, e to the x times secant of e to the x times tangent e to the x. Questions on that? Hopefully it's starting to make sense, but there, you know, there's infinitely many examples we could work. There's no way we could cover all possibilities. Example number 5, that's something that involves two chain rules. So we have an inner function being sine x, but then after we compute sine, we then have to raise that to the power, or e to that power. So there's two functions right there already. And then after we do that, we have to evaluate cosine of it. So there's 3 things going on here. So if we're going to be using, if we're going to use version 1, essentially what's going to happen is you're going to have to make 2 different substitutions. So version 1, we would say, all right, well, I'm going to let u be the inner function, and that, for now at least, seems like it's sine of x. Rewrite y in terms of our substitution. So that means y is equal to the cosine of e to the u. So this is why I think the second version is better once you kind of get the hang of it, because it's super long to do this, to take this derivative with the first version. Okay. We can take the derivative of u well enough. Derivative of u with respect to x, derivative of sine is cosine. But now we have to take the derivative of y in terms of u and multiply it by this cosine here. So taking the derivative of this cosine of e to the u is another substitution, right? So I don't know, maybe to take this derivative, we're going to let v equal e to the u, and then we have to take the derivative of that. And now you have 3 things you got to multiply. So it gets super messy, super quick. If you want to try that with, if you want to try to finish that with version 1, then go ahead. We're gonna validate or verify what the derivative actually is. So ... More work is needed there. I think with version 2 and us being able to write out derivative whenever we say or think derivative for the formula is going to be a lot easier here. So we say, in order to take the derivative of y, I'm going to take the derivative of my outside function and leave the inside function alone. So if I take the derivative of the outer function and leave the inside function alone, what is that going to look like? So what would our outer function be on y? Well, sine x is the innermost function, right? Because if you plug a value in for x, you got to do that first. What's the outermost function?
Oh, the cosine.
Yeah, cosine. So when we say take the derivative of the outer function, we mean take the derivative of cosine, and we leave the inside function alone. The inside function is e to the sine of x. Okay, so there's the derivative of the outer function with the inner function left alone. And then we got to do what? Yeah, we've got to multiply all of that by the derivative of the inside function. Does that make sense? Any questions at all? So that's not quite our derivative. We've got another derivative to figure out. So, excuse me, we're just going to take this thing here and off to the side, look down below, somewhere else. We're going to just kind of start over like this is an entirely new problem. We're not really thinking about that stuff up there anymore. We've got to address this derivative and then put that in place of that notation up there. So we have a second chain rule that we have to use for this derivative. We've already done this, but again, derivative of the outside function, leaving the inside function alone. And then we have to multiply that by the derivative of the inside. So we have cosine derivative of this, cosine times e to the sine. Remember, the derivative of, here we can think about the derivative of e to any power is just e to that power times the derivative of the power. Either way, you're using the chain rule. So cosine x times e to the sine x needs to go in for this derivative here. We're multiplying that by the negative sign of the quantity e to the sine x. That's pretty much the derivative. We could like rearrange how things are multiplied, but that's the main idea. Does anyone have questions about that? So these can get like pretty involved pretty quickly. And you just want to be careful here because there might be a tendency for you to combine these e to the, you say, well, I've got two things of e to the sine x being multiplied together. That's not the case because this e to the sine x, and we have here in black, is the argument of sine. So it can't come out. It's like the sign of that quantity. So we just have to leave them as they are. We have our negative sign of e to the sine x. So like that's one whole thing in and of itself, times our cosine times e to the sine. So these things are all kind of separate factors, but the derivative is all three of those things multiplied together. It doesn't really matter where this negative goes. You could attach that to any factor, but the other ones, the sine, the cosine, and the e to the sine, they have to stay as is. There's nothing you can do with that. This is our side book here. Does anyone have any questions? All right, so why don't y'all take about 8 minutes, find the derivative of the cosine of 19e to the x. Sorry.
I'm missing like polar. Sure. I think I'm missing something.
Yeah.
For some reason, I feel like I'm missing something at the end. That's good?
Yeah.
Okay.
Yeah.
Yeah.
So once you get to this point, you're like, okay, well, there's really no other derivatives left except for that, which is that. Yeah, so that's probably why it feels like
Weird.
unfulfilled.
Okay. Okay.
Yeah.
No, I just wrote it.
Yeah, because I think it's exponential. So it's still gonna like it's just yeah. So like usually all the other functions change so much. It's like because that function is still completely different, but I think it's probably just like it feels like it sounds more quick. Right here.
It's just derivative.
So it's the outermost times the derivative of the inside. Well, derivative of the outside times the inside.
Once you times the inside, then do the derivative of the next opposite.
Yep.
That's how it is.
Okay.
Or you could do it monochrome.
That's all you're doing is you're literally the function you're doing, the very beginning part, under the first part, multiplied by it's already there. And then pull everything into its opposite side, so you can know what's cosine is the derivative of the just rewrite it out. Derivative of the last derivative of 9.
Oh, okay. That makes sense.
So that's what it was.
So basically, since you're okay.
That's what I was writing down. So you can tell it's circle each thing. So okay, here's the dirt, this stuff, let's circle that. Apply it to the dribble. Times everything else. Circle that. This stuff. Circle that. Just have everything in a circle. Bring it down. I was trying to find the derivatives of these things.
Yes.
Oh, for catch.
Yes. I would say write it out first. So you know what else.
It's so messed up. Passing this class would be going to see chemistry B plus and public speaking.
Oh, no, that's just the same.
Where do you see the targets?
Tool writing. Drag on
I have no idea. You said you were there. You said you was going for
I just took this.
just started transferring this state.
I technically don't need this for my degree, but I'm doing it anyway. I have to go. More expensive than Singapore. I don't know that we were trying to that. Where'd you get that sweatshirt? I kind of dig that.
An engineering foundation. They don't sell them anymore. So I know this one's all like shredded up.
Kind of.
Says that your punisher he was.
I have two he was swaying. I'm not entirely sure it started.
So you want to see the derivative of like that?
I installed the new software. I might write it down. I'll let you know. What team were you?
That's just off the top of my head.
I have that.
Do this derivative, maybe separate it.
I think I color. Blue. 70? Blue. Oh, you're in blue.
Multiple efforts.
I'm in the yellow. There's no blue in the other. It's red, it's the most common, and then blue, and then but I get them now, when like I picked them. I used to have to do like cool 16 or something.
Alright, so like.
I mean, like,
Just like this, so this is all one function.
Well, my whole
Take the
family.
derivative of
My brothers. Well, my cousins.
derivative goes into the negative sign.
Yeah,
When we go, so you have a negative sign, inner function here.
I know.
So you still have a negative sign of all of
I
this
can't remember which
times the derivative of all of this.
I don't remember which crush is on,
So,
but
like,
I bet it's not this guy. It's just sad, but like in the rain, it's like, you know, on
So
my
you have the
side, you
derivative
know?
of the outside with the
No,
inside
yeah,
function
right.
left alone.
But we
You
make
gotta
sure
multiply
like
that,
that.
always gotta multiply it, like it's in the single constant.
You can want to go channels. Go to rates. Oh, I can be on.
Oh, yeah, sorry.
So for this question, it says, which is the lowest? Is it the same? Is it the same as like which was?
Yeah.
Okay.
This one.
Yeah.
That's what I want.
The reason that
So you, so like I would just grab that derivative.
One
I'm
question.
not sure why they have
There's
this.
Yeah.
Oh, this is kind of the same. It's 13 over 15. There's really, the lowest part is when the word crosses the line. Yeah. Or it just kind of curves, it starts flat, and then it goes like this. So it's never gonna reach the highest point, but the lowest point is gonna be right here where it crosses the axis, because that's when t equals 0.
Like the last one that we did.
Yeah.
Okay.
Yeah.
I moved that to
All right, here's the outermost function. So we take the derivative of the outermost function, and we have to leave the inside function alone. So we're leaving the cosine of, and you might not have to put as many parentheses. I'm just kind of trying to show you like, what we're taking, what's being put inside of what basically. So it's the negative sign, derivative of the outermost function, with our inner function left alone. And then we have, so it's the sign of this quantity. So it's the sign of that times the derivative of that. So I don't know, we'll just say times the derivative of this. And that's all the chain rule tells us to do, right? That's the chain rule. But then we say, well, I've got another derivative. I've already taken the derivative, but it just so happens another derivative has shown up. So I'll just take this and find its derivative somewhere else. So I wouldn't recommend trying to do it all at once. If you're awesome like that, then you go for it. So we'll do that here. Take the derivative of cosine of 19e to the x. So again, we're taking the cosine of that quantity. So the outermost function again is going to be cosine. Derivative is negative sine. Leaving the inside alone. And multiplying that by the derivative of the inside once again. Derivative of the inside is the derivative of 19e to the x. So with multiple chain rules especially, it can be really hard to determine, well, when do I stop taking derivatives? So that's why I recommend saying the rule, writing out derivative explicitly when you say derivative, and then any other derivatives that show up, just take them off to the side, because you'll know when you're done with those derivatives, and then you just plug those back into your original. So I've got another derivative showing up, like in effect, I would take that off to the side and say, well, is there another chain rule happening here, or what's happening here? It doesn't really matter, because I'm going to take the derivative of it. And then if I have other derivatives showing up, I'm just going to go below that, take their derivatives, and then just sort of like build back up, plug all of that stuff back into all of that stuff.
How many steps are, what's the maximum amount of steps you're gonna make us do to solve this?
Probably something like 3, like this one.
Okay.
Yeah. I think anything else gets a little bit overwhelming. So what we have negative sine of that quantity. But I mean, most of y'all did it correctly, and it didn't take you very long at all, considering you're just now learning this stuff. So, I mean, I think that's something to be said about that. I think that's impressive. And I think if I gave you one that had 4 chain rules, that you could do it.
Do we want
I won't. Right, yeah. Who don't want to do any of it, right? So we're multiplying negative sine of that quantity by 19e to the x. And again, all these rules floating around, 19e to the x, that's a product, right? So I apply the product rule. Like, you can totally do that, or you can recognize that 19 isn't a function of x, it's a constant times a function of x, so that 19 just comes out to multiply the derivative of e to the x. So however you want to think of that, I don't think there's a right way to think of it, but constant times a function of x, a lot more efficient than using the product rule. So the derivative of cosine of 19e to the x was this thing. It had another derivative that we computed here, so we just plugged that in place. Now we're looking at this thing right here and saying, well, hey, there's no derivatives left to take. That's how I know I'm done with that derivative. So what was this derivative? It's all of this stuff right here that we have circled. So we have all of this stuff here that we have circled, times all of that stuff we had originally present. I mean, it just looks funky because it's a funky function. Like, it's multiple functions inside functions. Times this thing right here. So again, we've got a negative sign of all of this stuff right here. That's one factor in and of itself. Negative sign of 19e to the x is another factor, and then the 19e to the x is the third factor. We could multiply these two negatives together just to kind of clean that up a bit and put the 19e to the x out front. But that's, that's pretty much all I would be looking for. So we have 19e to the x times sine of all of this stuff. you may or may not see all these parentheses in my math lab, so just be mindful of that. Times the sine of 19e to the x. And we'll put parentheses here too, just to, so we're clear what we're taking the sine of. So are there any questions? Yeah.
Shouldn't those signs be negative?
No, because we had this negative
Times that negative?
times that one, yeah. Yeah. So if you just left it like here, this step when we have on the exam, I would be fine with that.
Do you know how my math lab wants it?
I think it'll take it either way because they're all multiplied together. So you just gotta, make sure that you're specifying like what you're taking the sine or the cosine of, because it's sort of ambiguous if you write sine of cosine of 19e to the x. That's not really clear. It could be, it's, I don't know. I think it tends to confuse people too when you just write it like this. I mean, if you're okay with it, then that's fine. There's really only one input. So it must be that we're taking the sine of all of that. It's sort of implied, but I don't know. I always prefer to do that just to make sure. But it doesn't matter. Like what order you have this, you could have this thing, you could have that thing in the middle. You could have your sine of 19e to the x over here. And you could have your 19e to the x. Oops. You could have your 19e to the x over here, and that would be fine as well.
Would we have to simplify it? Because sometimes, like, I don't know about this one, but like for other classes, it wants you to get the most simplified version.
Yeah, honestly, it should say, I know it doesn't sometimes. If it's like, it doesn't like an answer, sometimes it's hard to tell, like, is it because I'm wrong, or is it because it wants a simpler version of this? But it should say, like, simplify your result.
Okay.
And if it doesn't, then something like that's fine. You can't simplify this anyways, other than multiplying the negatives. But other things, I don't think it's gonna, other things like similar to this, it's gonna be picky about it.
Okay.
With like expanding polynomials, combining like terms, those are things that it's probably gonna want. It's hard for me to know because it seems really random. Like sometimes it's fine if you just like enter a bunch of stuff and don't do anything with it, and sometimes it doesn't like it. So I don't know. I can't really answer that question 100%. Okay. Does anyone have any other questions on the chain rule? So we're gonna take a break, but in preparation for the next section, let me just ask one more question. If I told you like y is equal to some function of x squared, what's the derivative of that function? What's the derivative of y?
2 times f of x.
2 times f of x. Do y'all agree?
Times f prime x.
Times f prime, right? The chain rule says we have to multiply that by f prime. So this is like, well, the way we're looking at this, it's some function of x being squared. So we take the derivative of the outer and leave the inner function alone, and then we multiply it by the derivative of the inner. Does that make sense? Does anyone have any questions on that? Okay, so if that makes sense, then you know exactly how to do all of the stuff in 3.8, because that's the same idea that section 3.8 is based off of. So it's implicit differentiation. Okay, well, we'll take a break and then start 3.8.
I don't know.
All right. So, yeah, section 3.8, we're going to look at implicit differentiation. So you can think of what we've been doing up to now as like explicit differentiation, because the functions have been explicitly solved for y. So we've explicitly looked at derivatives of y equals to a function of x. Functions defined implicitly, like x squared plus y squared equals 1, or sine of x cubed y squared minus 3y equals 5. Those are implicitly defined functions because it's sort of implying what the function of x is, just not explicitly stating it. Something like x squared plus y squared equals 1, you can solve for y. Something like example 2 with sine of x cubed y squared, you cannot solve for y. So that's the big advantage of being able to do implicit differentiation is something like sine of x cubed y squared minus 3y equals 5. We can still find the derivative of that without ever having to solve for y explicitly. So, you know, just one example of why we need a different method to find y prime. When we find derivatives implicitly here, we have to remember that whenever we see a y, that it really represents an unknown function of x because we haven't solved for it. When we get to section 311 and start relating rates, the variable there is time, so we implicitly differentiate with respect to time. So in most of the time for us though, y is a function of x, whether we can solve for it or not. Okay. So what we're going to start off with is taking an example like x squared plus y squared equals 1, being able to solve for y, sort of, we'll use this example to show that if we solve for y first and then find its derivative, that it will match with taking the derivative implicitly. That way we can sort of have a little faith that the method does actually work. And we're going to, again, motivate it with this specific example. So find the derivative explicitly. That means we're going to have to solve for y. So we subtract x squared, and then we take the positive and the negative square root of both sides. So by the way, x squared plus y squared equals 1. What kind of graph is that? A circle with a center at 0, 0, and its radius is 1. So that's the unit circle. And so once we find the derivative, we should be able to find the slope of that circle at any given point on the circle. But the issue with this is we've got, essentially, there's two different representations for y. So one, we've got to look at y being the square root of 1 minus x squared, and y being the negative square root of 1 minus x squared. So in order to take the derivative of y equals the square root of that quantity, we're going to think about it as 1 minus x squared to the power of 1/2. And then just use our chain rule to take its derivative. So y prime is going to be 1/2 times 1 minus x squared to the negative 1/2. Again, that's the derivative of the outer function with the inner function left alone. And then we have to multiply that by the derivative of the inner function. So it's that times the derivative of 1 minus x squared, which is minus 2x. In other words, y prime is negative x times 1 minus x squared to the negative 1/2. And we're going to write that with positive exponents. So the square root's on bottom. So our chain rule, we simplified, we wrote with positive exponents. So there's y prime for, maybe we should ask, this is the derivative for what? We already said that x squared plus y squared was the unit circle. Y prime in this representation would tell us the slope of the tangent line where? On the upper half of the circle. We know that because the square root's positive. So y is the positive square root. Y is positive at all of these values. The second one is going to tell us the slopes of the tangent line on the bottom half of the circle when y is negative. Which one of these would tell us the slope of the tangent line at the ends, I guess? So what's the slope of the tangent line at that point and at that point on the circle? What's the slope of that vertical line? It's undefined, right? Vertical lines have undefined slope. So we might say, well, which one of these gives us the slope at x equal to -1 and x equal to +1? You can just look at the derivative itself. X over the square root of 1 minus x squared. Is that derivative defined at 1 or -1? No, because if we plug in x equals 1 or -1 into our derivative, we're dividing by 0. It's undefined. Undefined in the sense that we have a vertical tangent. So the second derivative here, the second function or whatever, its derivative, since the function is just the opposite of this function, we just have an extra minus floating around, right? So the only difference between the derivatives is the minus sign. So I mean, we could go through all of that. It's exactly the same though. The derivative of this second bottom half of the circle, if you will, is positive x over the square root of 1 minus x squared. So again, that derivative there, the positive x over the square root, that gives us the slope of the tangent line at all points on the bottom half of the circle. The derivative is defined for all x for all x not equal to positive and -1. Like we saw, we have vertical tangents there. Vertical tangent lines. So is that all right? Any questions on either of those derivatives? We said, here's something defined implicitly. We solved it explicitly, took the derivative. We have these two derivatives. Okay, so everyone's okay with that? Then we'll look at the implicit derivative of x squared plus y squared equals to 1. Remember, implicitly, we're not going to try to solve for y at all. But you have to remember that y is some function of x. So when we look at the equation x squared plus y squared equals to 1, you know, maybe you want to write it out this way or just think about it in your head this way. But either way, this is what we're looking at. We're looking at x squared plus y squared equals to 1, where y is some function of x. What function that is, we know because we were able to solve for y previously. For most of these, you're not going to know. So we're just going to think of it that way. Y is really f of x. So when I take the derivative, what's the derivative of x squared? 2x. Plus the derivative of y squared. What's the derivative of y squared?
2f of x times.
Yes. Times y prime, right? It's 2y, y prime. Derivative of the outer function, leaving the inner function alone, that's a 1, times the derivative of the inner function. Okay. Just like over here, like what we said before we went on break, the derivative is 2x plus 2 times f of x times f prime. So there's your 2y, y prime. Does that make sense? So every time you take a derivative of something with y, with respect to x, you're going to take it normally, but then you're going to multiply it by a y prime. That's kind of all this section boils down to. Equals to the derivative of the right-hand side of our equation, the derivative of 1 is 0. But that's not the derivative, is it? The derivative is represented by y prime. So now we solve for y prime. Divide both sides by 2. We have x plus y, y prime is equal to 0. Subtract x. And then divide by y. So since we never solved for y, we don't have at least initially here, we don't have a means to know what that is. But if I said find the slope of the tangent line at this point, x comma y, then you just plug the x and the y into this derivative formula. Up till now, we were plugging just the x value into the derivative formula because it was explicit. So there's the derivative implicitly, and if we look at the derivative that we found explicitly, we had two representations. Y was the negative x over the square root of 1 minus x squared, or positive x over the square root of 1 minus x squared. So they definitely don't look the same, but we have to remember in this explicit formula from x squared y plus y squared equals to 1, when we solved for y, we had that y was plus minus square root of 1 minus x squared. Yeah? So isn't this just y here? And isn't that just y there? Or negative y, right? This is really negative y. So you have, this is really x over y. So let me rewrite that. That's negative x over y. And the other one, we have positive x over negative y, which is the same thing. So either way we look at it, isn't it still negative x over y? So in both instances are summarized right here. So that, again, that example is just illustrating that the derivatives are consistent. Does anyone have any questions on that? Okay, so let's just look at maybe one or two numerical examples here with the same function, the same derivative. So find the slope of the tangent line at, we'll look at just 2 points. At 1, the point will be 1/2 comma root 3 over 2. And second point, we'll look at it at 1/2 negative root 3 over 2. We've got two derivatives, the explicit one and the implicit one. So use whichever one you want. Oh, I already have that down here. I'll just erase that down below. If we're going to use y prime as negative x over y, or negative x over y times negative 1, however you want to think of it, we're just going to plug in both of these into that formula. So the slope of the tangent line at 1/2 root 3 over 2 is the negative of 1/2 divided by the y value, root 3 over 2. So that's really the only difference. Most of these implicit derivatives will involve both x and y. All right, so we have negative, right here, we have negative 1 over root 3 for that one. That's the slope of the tangent line at that point. Or negative root 3 over 3. And y prime at the second point, we have our negative x over y. And that's just 1 over root 3, or root 3 over 3. Sorry to have that, but just want to make that cut off. All right, so points on the circle, that's their slopes.
How did you use the equation? Why
At this point, it didn't matter because we either had an implicit derivative, we could have plugged our x and y coordinates into that, Or we could have said, well, the point 1/2 root 3 over 2, that's on the top half of the circle. So I could have just plugged the 1/2 into this derivative here. And for the second point with the negative 1/2, that's the bottom half of the circle. I could have just plugged in the negative 1/2 into that one. You would get the same exact answer. Yeah. But for what we're doing moving forward, we're not going to have this explicit representation of the derivative. Yeah, so at the point 1/2 root 3 over 2, it's here. We said that the slope was negative 1 over root 3. So we can see, of course, at this point, the slope of the tangent line is negative. At negative 1/2 root 3 over 2, at this point, we can see that the slope is positive. We also did mention that at this point and at this point, the derivative is not defined. So we have our vertical tangents there at this point and that point. What about these 2 points?
0.
We should have our derivative being 0, right? Because at both of those points, x is 0. Doesn't matter what y is, when we see the derivative as negative x over y is not 0, but x is, so that quotient is going to be 0 at both of those points. Or the slope of the tangent line is 0. All right, so it all sort of, validates that implicit differentiation is a legitimate differentiation tool, I guess. Are there any questions on what we've done? Okay. Yeah. Were they? I don't know. Oh yeah, they were both.
Positive 1/2.
They were both positive 1/2s. Yeah, so this point, get rid of it and plot the appropriate point. It's still going to be positive. Yeah, sorry, that was negative 1/2 negative negative root 3 over 2. So we had, the other point was actually 1/2 negative root 3 over 2. So that slope is positive root 3 over 3. Sorry about that. Thanks for noticing. All right, any other questions or comments? So find the derivative of x squared plus xy minus y cubed equals 7. This is the curve represented by that equation. So we're going to take the derivative. And that's the nice thing also about implicit differentiation. You don't have to solve for anything. You can just start taking the derivative of stuff. So the derivative of x squared plus the derivative, what's the derivative of xy? Y prime? What do y'all think? 1? Y prime? If I told you to take the derivative of this, what would you do? What rule would you use?
Chain.
Product though, right? It's x times another function of x. If I told you to take the derivative of this, right, you'd use a product rule. If I told you to take the derivative of this, you would use a product rule. So this is a product rule. That's a product rule. So we've got a product rule there. We'll look at that in a second, I guess. What's the derivative of our negative y cubed?
Wouldn't that be negative 3y times y prime by 2, or negative 3y squared times
Yeah.
y prime?
Negative
Yes.
3y squared times y prime. So we take the derivative of y, like we would with x, right? But then we just multiply that by the derivative of y. That's the chain rule. Okay, so derivative of y cubed is 3y squared times y prime. Does that make sense? Anybody have any questions? Okay, we're just looking at it as some function of x cubed. And using the chain rule. Equals the derivative of 7, which still, again, is 0. Yeah, I didn't leave enough space. But over here, let's take the derivative of xy. So it's a product rule. We have the first times the derivative of the second. What's the derivative of y?
Y prime.
Y prime. First times the derivative of the second plus the second times the derivative of x is 1. So there's the derivative of xy. Xy prime plus y. All right, any questions on what we've done? So that's not quite the derivative. Now, again, we have to solve for our y prime. There's two types of questions. You see the equation, and it says just find the derivative, which you'll always have to solve for y prime if that's the case. If this question were to ask us, what's the slope of the tangent line at this point, then you don't really need to solve for y prime, because once they give you a point, you have an x and a y. So you can plug your x and y, if you're given a point, you can plug your x and y immediately into this equation here, and then you'll just have one unknown as your y prime. You won't have x's, y's, and y primes that you have to keep track of. So after you plug an x and a y in, you'll just have y primes and numbers, and you can solve for y prime that way. So there's really two types of things. Some questions just have you find the derivative. Some questions have you find the derivative at a specific point. So we're going to solve for y prime. So all we're going to do is we're going to isolate the terms that have y prime. We want those together on one side. So we want our our xy prime and our negative 3y squared y prime. We want those two together. We want everything else on the other side of the equation. Because from here, what are we going to do? Yeah, isolate y prime by factoring y prime out. Now both of these terms have a y prime. We're just going to factor that out. We have y prime times the quantity x minus 3y squared equals to our negative 2x minus y. Now we have y prime times something, we're going to just divide by that to solve for y prime. And that's our derivative. So all of these are, take varying forms, but that's the idea. To solve for y prime, you isolate the terms with y prime and then factor it out, divide through by what's remaining. So there's our derivative. Any questions on that? So we can look at one where we have or we'll stick with this one and look at it at a specific point. So we'll find the slope of the tangent line at this point, 3, 2. Make some space here. So that could be like one version of the question, and the other version could be find the slope of the tangent line. Find the slope of the tangent line of our same function. At the point 3, 2. Okay, so honestly, I think it's a little less confusing when you're asked to find the slope at a point, to not solve for the derivative entirely like we did here, but to just find the derivative in this type of situation, plug in x and y at that juncture, I guess, point. So there was our derivative. So, oops. Instead of solving for y prime here, there's our derivative. We're just going to plug in x and y first. Derivative is this. X is 3, y is 2.
I think you need a square still.
Oh, square. Yeah? Yeah. Okay. So x is 3. Y is 2. And so from there we can figure out, like, we're going to see how many y primes we have and how many other things we have. We have 6 plus 3y prime plus 2 minus 12y prime is equal to 0. And then then we're combining like terms. Minus 9y prime plus 8 is equal to 0. So we have our 9y prime equals to 8, or y prime is 8 over 9. So that's the slope of that curve at the point 3, 2. So that might be a little bit easier to just work with numbers in y prime versus x's, y's, and y primes. But that only happens when they ask you to find the slope at a point. If you're asked to just find the derivative, you've got to solve. Does that make sense? Anyone have any questions about that? And we could certainly check with the derivative, since we had already found the derivative, we could certainly check if I plug in x equals 3 and y equals 2 in that, we should come out with 8/9. So minus 2x. That was the derivative, right?
Mm-hmm.
Okay. So check y prime from our original step at the point 3, 2. We're just going to use this formula instead. And you don't have to do it both ways, right? One way is fine. We're just trying to validate that we've done the correct stuff throughout this process. We have minus 2 times x minus y all over our x minus 3y squared. Okay, so that's up top, minus 6 minus 2. We've got a 3 minus 12. So slope is 8/9 at that point 3, 2. If we needed the equation of the tangent line, we've got our slope, we've got our point, we put that in point slope formula. So all of that stuff still applies. Any questions on that derivative? So here we want to find the equation of the tangent line on this thing at the point 1, 1. So now we're asked to find, basically we've got to find the slope of the tangent line at that point. So really, there's no need to solve for y prime in terms of x and y. We can find first the derivative. What's the derivative of x to the 2/3? Two-thirds x to the negative 1/3, right, when we subtract 1. 2/3 x to the negative 1/3 plus the derivative of y to the 2/3. What's the derivative of y to the 2/3?
2/3 y to the negative 1/3 y prime.
Yep. 2/3 y to the negative 1/3 times y prime. Equals to the derivative of 2, which is 0. Don't forget to take the derivative of both sides. Things wouldn't work out if you left that other side as 2. I mean, we could solve for y prime and then plug in 1, 1. Or we could just do it now. It doesn't matter. have, let's say the slope of the tangent line at 1, 1. I mean, I don't know that we really have to do much here, but we're going to show this anyways. So we have 2/3 for this one, plus 2/3 y prime for this one, is equal to 0. And then from here, we're solving for y prime. So we have y prime is equal to -1. And that's the slope of the tangent line on that, whatever, diamond shape at 1, 1. Any questions on that? Yeah.
What happened to your -1/3?
Negative 1/3?
I mean, it was wasted.
Oh, once we plugged in 1, it went away because 1 to any power was just itself. Yeah, because remember 1 to the negative 1/3 power is the same thing as 1 over 1 to the positive 1/3, which is 1 over the cube root of 1. All right, so slope of the tangent line at the point, equation of the tangent line at the point, equation of the tangent line, y minus the y coordinate equals to the slope of the tangent line at that point times x minus the x coordinate. We have a -1 plus 1, positive 1, positive 1. So there's the equation of the tangent line. So, a lot of these things aren't functions. This definitely not a function. So we found that equation to be -x plus 2. I mean, it crosses here and here, but at that value, we know exactly how steep that is. It's -1. I guess it's time to go. Everybody packing up. Look, we probably don't want to start another example anyways. We've got 3 minutes, so. Hey, y'all have a good weekend.